Hey, in this video, I made a little question, and it's regarding flattening out a coin like this. It says a coin 6 millimeters thick and 38 millimeters in diameter is formed into a square sheet, 0.01 millimeters thick. How wide is it? So how wide is the square sheet? And then it gives a few decimals of pi. So I just wrote up this problem this evening, and I didn't have an answer or anything. I just here trying to figure it out. And yeah, I'm just initially trying to think about the problem, what I think I need to do. I think I need to find the radius as a function of ice crossroad volume. So height. Okay, so I'm kind of trying to figure out how to figure out this problem. So anyway, this is just me in the background working on it. I guess this whole idea of squishing a coin, um, I heard a remarkable property of silver that it's very malleable. So that means it can be hammered or rolled into thin sheets without breaking. That's different from ductility, which is the ability to be stretched into a wire. So this idea is that the coin would be like thinned out. So I got here width of the squared circle is the square root of the area. So again, so if like let's not think about the coin for a second. If it's just like a flat surface, like a circle, that's the surface area is the area. So if you have some sort of area like a blob or a circle, and you find the square root of it, you're going to get a square, and you're going to get the length of the side. So we know you have to find the square root of an area. So the area is what we're looking for. Yeah, so 38 millimeter diameter. Again, obviously metric for any American watchers. 1 meter. Then you have a decimeter, which is at 0.1 meters, or a tenth of a meter. A centimeter, there's 100 centimeters in a meter, and a millimeter, there's 10 millimeters in a centimeter, so micrometer. So I mean, we're talking about silver can be hammered out into like 0.2 or 0.3 micrometers, depending on techniques. It can get a little thinner, but yeah, so it's being 30 going into 0.01 millimeters is definitely realistic. Okay, so yeah. Okay, obviously area pi r squared. So what the correct approach is here is that we are going to try to find what is the actual volume of the coin, and then we're going to find what would be the area once we squish that volume to 0.01 millimeters. I think at some point, the silver or substance would begin developing tiny tears if like the crystal structure was hammered thinner and thinner, and it would just lose its mechanical integrity. All right, so you see here, I got the volume. Volume is of course pi r squared times the height. So we already know the height, we already know the radius. We can find the actual volume of the coin. I mean, every atom of silver on Earth was forged in one of the most violent events the universe has ever produced. Of course, silver is too heavy to be made in the ordinary nuclear furnaces of stars. Instead, it's created during the rapid neutron capture process, or reprocess, when atomic nuclei are bombarded by an enormous flood of neutrons in just fractions of a second. One of the main places we understand this happens is during the collision of two neutron stars. So two objects more massive than the sun, but only 20 kilometers across. Spiral around each other hundreds of thousands of times each second. As they emerge, space ripples into gravitational waves, temperatures soar to billions of degrees, and matter exists not as ordinary solids or liquids, but incredibly dense, incandescent plasma. The collision ejects materials at a significant fraction of the speed of light, creating brilliant explosions called kilonova. Within this, so here in the problem, sorry, I'm getting a little I'm trying to figure it out. I'm like a little lost and confused. Um, I know I got some things right here, and turns out I did when I checked afterwards, but I was trying to figure it out. So, kilonova, within the expanding cloud, atomic nuclei are bombarded by torrents of neutrons, far more quickly than they can decay. So, in mere moments, lighter nuclei are transformed into some of the universe's heaviest elements, including silver. As the cloud expands and cools over days and weeks, newly formed atoms stabilize and eventually become tiny grains of matter drifting through space. All right, so the problem I correctly did it. Area as a function of the height. So you have to divide by the height just to find basically the length and width, or the pi r squared surface area. So we have the area, then we can find the square root of it. So billions of years later, after that stardust became part of the cloud that formed our solar system. So the silver in a coin, uh, or whatever electrical item we have, was once part of the cosmic debris. It was asking me to do, it's really asking me to multiply out pi times this number. I'm like, oh man. So I'm just about to give up. I'm like, oh, maybe I should give up on this problem. Like, anyway, but I'm like, I just take a minute to process. And eventually I'm okay and go forward with it. All right, electrical conductivity. Silver is the most electrically conductive element known, with a conductivity about 5% higher than copper. Well, 5%, I mean, it's not so huge, you would say, like, I mean, you could use copper instead of silver. But since almost all electrical wiring is made from copper instead, but copper is just much less expensive, it's much more abundant, nearly as conductive, making it a practical choice for most applications. But silver is reserved for situations where maximum performance is worth the cost. It's used in high performance electrical contacts like aerospace systems, satellite communications, radio frequency equipment, and precision instruments. It also has the highest thermal conductivity of any metal, making it excellent at dissipating heat. So there are other conductive materials, of course. Gold, it conducts electricity very well, resists corrosion. Aluminum is lighter and cheaper than copper. It's commonly used in overhead power lines. Carbon-based materials are also remarkable, like graphite conductors conduct electricity. Graphene, a single layer of carbon atoms, is also a promising material for future high-speed electronics. All right, light reflectivity. Silver is also the most reflective element known, reflecting about 95 to 99% of visible light when freshly polished. So that's interesting. It's the most electrically conductive material and the most reflective element known. Reflecting 95 to 99% visible light when freshly polished. This makes it the material of choice for high quality mirrors, precision optics, instruments. Aluminum Aluminum is close second. It's often preferred for telescopic mirrors because it's lighter and less expensive. Um, Also resists corrosion better. All right. So I got my area. Looks like it is 680,000 millimeters. Now the question is, how big is this square? Square side. History as money. For much of human history, silver was money. Beginning around the 7th century BC, kingdoms in Lydia, modern-day Turkey, and later the Greek city-states began minting standardized silver coins. Because silver was scarce, durable, divisible, and easy to recognize, it became an ideal store of wealth. That's cool. It's kind of, I think, it's a reference to Aristotle. Money, scarce, durable, divisible. Yeah, it stores wealth. Unlike grain or livestock, it didn't spoil, and unlike paper money, it had intrinsic value. Romans later adopted the denarius, a silver coin that became one of the most widely circulated currencies in the ancient world. For centuries, wages, taxes, and international trade were often measured in silver. Of course, it's been used uh, for purchasing power across the known world, but there is a point about debasement. Um, so here I'm just going to calculate the square root of 687,000. For this part, I guess maybe I should say I commented about it. I've seen, definitely there's better videos on YouTube about how to do this, but I had to look at a few different videos to see some of the details. So first I'm counting in the numbers in blocks of 2, and then you go start from the left, and you take a block, whether it's a single number or if it's an odd number of digits, it'll be one number or it's two numbers on the left. You look for the biggest square that fits in it. In this case, 8 times 8 is 64. So it goes inside the 68. So you could have like 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. So the biggest number that can fit into that 68. And on the left side, you'll see that I added that number to itself. So that's the first number that goes on the top. 8 times 8 is 64. The 8, then you plus 8. So whatever number you find there, you're going to plus it to itself. And you draw it kind of at an angle underneath. So you get 8 plus 8 is 16. And you put a box there, and a box there, and a box where you put it. So that's going to be the same number. Like 163 times 3, 162 times 2, 161 times 1. It's going to be the same number. So you have to figure out what that number is that fits underneath the 404 in this case. And then you subtract it, just very similar as division. So I had it kind of at an angle like that. 2 plus 2 is 4, and I put the 4 further to the left. And then I got to, again, figure out 164 something, so about 1600 fits into about 8,000. How many times? I'm just like guessing here, like, oh, maybe 4 times, 5 times. Then you can do out the math. And so 6576 does fit into 8,000. So that works. I was going to try 5 to check if maybe you can fit more into there. And 8,200, no, that's too big. It doesn't fit into 8,000. So that's why the next number in the square root can be 4. So 4 times 16, 44. Subtract that. And on the left, we're going to add it. To do the next line, leave a space for the numbers. So subtract these. Always bring down the numbers in blocks of 2. And I add the commas at the end there after I bring down the number, so I can see it's about 16,000 into about 149,000. In the Roman Empire's silver denarius began this high purity silver coin of about 95 to 98% silver in the early empire. Over the next 2 centuries, however, emperors gradually began to reduce its silver content, mixing it in increasing amounts of copper while issuing more coins. This process, known as debasement, that is like sort of like quantitative easing, I guess, allowed the government to finance wars, public works, and growing bureaucracy without raising taxes immediately. Consequences were significant. As people realized newer coins contained less silver, confidence in the currency declined. Prices rose, trade became more difficult, and many people preferred to hoard older, purer coins, a phenomenon later described as Grecian's law. Bad money drives out good. However, historians generally do not consider coin debasement to be the primary cause of the Rome's fall. It was one symptom of deeper structural problems. The empire also faced repeated civil wars, political instability, heavy taxation, military overspending, and population declines from epidemics, economic contraction, and increasing pressure from Germanic and Persian rivals. Okay, so silver debasement was an important contributing factor rather than decisive element. Fair enough. So numbers have a tricky way trying to figure out how many times 1,600,000 fits into 8,900,000. You know, it's sometimes pretty tricky to see how many times it fits in. Well, so I started talking about an ordinary coin and asked what would happen if I flattened it into a thin sheet of silver. So geometry kind of shows relationships that are not immediately visible. It gives a kind of math gives a way of seeing beneath the surface of everyday things. These atoms of silver were forged billions of years ago in one of the most violent events in the universe, probably like a collision of neutron stars, long before Earth existed. And those heavy elements eventually became part of our planet. And, uh, so I guess silver has like these remarkable physical properties. It's electrically conductive, the most electrically conductive, the most reflective, one of the most malleable metals. It's served as money, powered civilizations, and continues playing an important role in advanced technology. So it's kind of like history, but it's also cosmic history. Struggling a little bit with 16 into 69. So that's about a wrap. comes out to 824 millimeters, 824.9054. So yeah, I mean, that's like it's like almost a meter. A meter would be 1,000 millimeters, so it's like zero point 0.8 of a meter.